here, DBW0. The reason why there's a number there is because we might have more than one process, DBW1, DBW2, and so on. Okay, so this process is just responsible for writing information from the buffer cache to the database file, and it does it in blocks. Remember, everything is done in blocks, not records. The database writer does not continually write blocks from the buffer cache to the database file. Instead, it writes it out, it flushes it out on a regular basis in intervals, or when the buffer cache becomes a certain percentage full. And next to the database writer, we've got our checkpoint process. Now, a checkpoint is going to occur whenever the database writer flushes the buffer cache out to disk. A checkpoint also occurs on a regular basis defined by some initialization parameters, and also whenever redo logs become full and a redo log switch occurs. We'll talk about redo logs in just a moment. So all this checkpoint process does is it updates the data file headers. So everything in the database is synchronized. Next, we've got our log writer. That's writing log buffer data to the redo logs. Do you see how I just added another redo log there? The reason for that is that we need to always have at least 2 redo logs. Once one of them gets filled up, then the other will get written to. Once that's filled up, then it writes in a circular fashion back to the other one. Now, if we have archiving turned on, then before a redo log is overwritten, it's going to save that information to the archive log. Now, if you don't care about your data, then don't turn on archiving. For example, if you're in a test environment or a development environment, it doesn't really matter. Save the disk space. And once again, the only purpose of our redo logs is to perform recovery. Next to our log writer process, we have our archiving process. You can have more than one, so they'd be ARC0, ARC1, ARC2, and so on. Notice there's not a star there because it's not a required process. If you have your archiving turned on, then that process will be there. We'll talk later where all these archive log files are going to go. Then we have PMON, or the process monitor. This is used for any of the user processes. If anything goes wrong, for example, if a session gets killed or it fails for some reason, then this PMON is going to come along and clean up any resources, clean up the cache. PMON is also going to start any server processes if they've failed. And then last but not least, we have SMON, which is the system monitor. It's going to perform instance recovery. So if you improperly shut your database down, like pulling out the plug without doing a shutdown statement, then when the database starts back up again, SMON is going to go ahead and clean things up for you. Now, as far as these background processes go, these are the main ones. These are the more common ones. There are some additional ones dealing with advanced queuing and streaming, but we won't get into that quite yet. I mentioned earlier that there are differences between Windows versus Unix and Linux when it comes to processes. If you're on a Windows system and you want to see my Oracle process is up and running, go ahead and hit Control-Alt-Delete to bring up this nice Windows Task Manager. And make sure you go to the Processes tab. You can sort the image name by an alphabetical order, and Oracle.exe is going to be one process that has multiple threads dealing with all the processes. Now, if you're on Unix or Linux, then issuing the ps-ef, pipe that to grep Oracle, that's going to list all of the processes that are owned by Oracle. So you're going to see multiple processes. You'll see one for SMON, PMON, log writer, database writer, and so on. Okay, let's talk about server processes. They're right up here. A server process is responsible for grabbing the information from the database. So the server process is going to be on the actual machine that the database is on. And so it can tap into the data files and grab what it needs, and it also puts that information into the buffer cache. Okay, so I'm just going to put a little dotted line here just to show you this side is the server, and now a user process is going to connect to a server process. Let me give you an example. If you're logging into SQL+, your SQL+ program is a user process. and that's going to connect to a server process, which in turn is going to grab your data for you and return it back to you. Now, all these server processes have their own separate little area of memory called the PGA. It doesn't stand for Pro Golf Association. It's actually the Program Global Area. And that PGA memory area just contains information about the session, such as variables and cursor state information. For example, the data coming back to the user. So let's say we've got 15 users that are trying to tap into the database with different programs. We might have several using SQL+, we might have a few using Toad, there might be a couple using a Java program or a Perl program. All of those are going to be aligned with the user process. Okay, there will be a user process for each one of those programs, and then, so if we have 15 users, we're going to have 15 server processes. Now, what I just described to you is what we call a dedicated server environment. That's the default installation for Oracle. There's another type of configuration called a shared server configuration. In previous versions of Oracle, shared server was otherwise known as MTS, or multi-threaded server. We will cover all the details about shared server architecture in another nugget. Let's talk about the physical structures of your database. Now, the physical structures are those that are real files that you can see on the OS level. Well, you're definitely going to have database files. The naming convention is to have them end in .dbf. These are binary files, so if you try to open them up with the text editor, you will not be able to read them. If you want to see what data files you have in your database, you can query a table called, it's actually a view, DBA data files. Okay, so the column in there is file name, and there's a column for bytes. I'm just dividing by 1024 twice so I can put this in megabytes. It's just easier to read. Okay, so let's execute this. I've got a really small database. On a live production system, it's not unusual to see files that are 5 or 6 gigabytes in size. I want you to pay attention to the naming convention. So here we've got our base directory of Oracle Product 10.2.0, and then underneath that you'll have ORA data, and then the name of your instance, and then the data file. That's a pretty strong naming convention. Do not veer from that. So on a particular machine, you might have more than one database. And so remember, each database is going to have its own particular name. And so then you can go through your operating system and tell just by the naming convention what it belongs to. And you can also find out when a file was created by querying the $$ data file view. Okay, so select name, creation time from $$ data file, and there we go. Let's look at our redo log files. Where do we find those? Well, we can query $$ log file to find out where they are. And once again, look, it's under your Oracle Home, ORA data, the name of your database, and then the name of the redo log. Now, each redo log file will belong to a group. And it's a good idea to have more than one redo log file per group for redundancy in case one of them fails, because those redo log files are very important. Remember what they do? They're used for instance recovery and other types of recovery. Let's look at another view called $$ log. This shows us information about our log groups. So once again, we have group numbers 1, 2, and 3. Then we have the sequence number. The sequence number is a unique identifier. Notice that it is incremented by 1 every time. And once our sequence number 10 redo log group is filled up, notice that this is the current one that's being written to right now. Once that's filled up, then the next one will be group number 1, and then its sequence number will be 11, and so on. So it does get written to in a circular fashion. Then we can see the size in bytes of each of our groups. You always want to have the members in a group be the same size, and you also want to have each of the groups be the same size. Then this column for archive just tells us yes or no. Has this been archived to an archive log? So our current one has not been archived yet. The status of inactive simply means that this redo log group will not be necessary if we need to do instance recovery. So at any given point, there's always going to be exactly one group that's going to be the current redo log group that's getting written to. The way I have my database set up right now, I have 3 redo log groups, and there's only one member in each group. Now, ideally, I'd like to have more than one member in each group, and have some mirroring going on.